We are live. Are we live on your channel as well, Alan?
Yes, sir.
All right, cool. I had some people in the chat. I don't see anyone in the view, but hopefully that'll catch up. All right, well, I guess welcome, Alan, also known as Space Audits, to the channel once again. Today, let's try something different, something we have not tried before, I think, which is that Alan is going to teach me how the ether vortex works, right?
Yeah.
Am I saying that right?
Yeah. So I'm gonna go over like a summation of the experiments of like where I'm coming from and show you like how what I'm drawing, my conclusions based on more or less. And you can agree with them or not, totally cool. And we could discuss the intricacies of them. I know for sure you want to get to the single axis gyro stuff probably.
Yeah.
Yeah.
The
Yeah.
main thing.
We can jump right into it. Yeah, let's go.
To summarize, the main thing that triggered this whole thing is you were on with McToon on Jaren's debate channel, right?
Mm-hmm.
And you guys were kind of, just reading off back and forth. And what I felt was lacking was we didn't have this opportunity to say, well, hold on, I don't understand that. Explain that part to me.
Yeah. Well, that's
and you had this diagram. So that's what we're doing here. You're going to explain how this works.
Yeah, absolutely. So in regards to the debate, yeah, McToon had every opportunity to question me during the cross-examination, but if you remember, he yielded his time, all 7 minutes of it.
Okay. All right. Yeah. Fair enough. So let me rephrase. I wasn't there to ask questions.
You would like clarification on it, and which I'm happy to provide. But yeah, more or less, yeah.
It was a debate. This is not a debate. See, I'm not trying to ask questions in order to prove that you're wrong, which is what he would have been doing.
Right.
I want to ask questions in order to completely understand what it is you're trying to explain.
Cool. All right. So with that, we can just jump right into it. So let's see here. So let's start with the single axis gyroscope stuff, right?
Okay. And you want to do some screen sharing? Okay. Yeah. Let me make you big.
Should be good to go.
How do I make you big? So low. Boom. I'm going to turn off my banner.
Cool.
So you have the whole screen.
All right. Cool. So for those of you guys who aren't familiar with the single axis gyro, do you mind if I give like a rendition of what we're all talking about for our audience? Like, okay, cool. So for those of you who aren't familiar with the single axis gyroscope situation and all that, the way that they say that the single axis gyro gets the best readings on the globe is that you have to have it axially aligned with the axis of rotation, right? It has to be parallel to that, right? So if you have a device like, say, for example, your cell phone on your desk, it's flat. If you wanted to align it, if you wanted to get a reading with Earth's rotation, you'd have to tilt it by 45 degrees, right? And that's kind of what this diagram is illustrating here. It's different orientations that the device would have to be if we live on a globe to be in alignment to get those best readings. How am I doing so far on the mainstream narrative of it?
Yep, that sounds right to me. I even have a very similar slide prepared myself. So awesome.
Awesome. Yeah. And then so we got this guy. So I started looking into single axis gyroscope correction angles and whatnot, because that would be an excellent supplementary proof for the globe if this was true, if you would get symmetrical readings at this location. Oh yeah. So that's the other part to this, right? So at the 45th latitude, right? Let's just say this is the 45th, right? So you would have to correct it by 45 degrees. And at around this latitude, they get a fringe reading of 7.5 degrees per hour, right? So when they take their initial reading, they get their 7.5.
No, it's not 7.5, but
yeah, well, I can show you the data that guy posted. It's pretty close.
0.7. It's 0.7 times 15, whatever that is.
Yeah, whatever it is, it averages out to 15 degrees per hour when you flip the device and take the inverted reading. They just add it out and then add it out and then average it out, right? So that's what they're doing there with the single axis. So this is a single axis sag-neck interferometer. So what it does here is it rotates 360 degrees clockwise and counterclockwise when it takes its readings. And then the orientation of the device, you see has it off-centered here. Off axis by 45 degrees. And this gentleman's location is in Toronto. So he's at about the 43rd parallel. So on the globe here, he's making that correction angle to be in alignment to get the best readings. And he was getting around, what was it, like 7 point something, like 7.5-ish. And then he published, or, he did the flip and then the averaging out and all that. And you can find all the data and all that stuff on his website.
Okay.
It's very, very cool.
Let me ask, are you saying he was not getting the 15 degrees per hour that he's supposed to get?
No, he got it.
Okay. Okay.
Yeah.
Okay.
Yeah, he got, so but it comes in the form of 2 readings though. Like, I don't know if you knew that, because I didn't know that. I thought that it was a single reading of 15 degrees per hour, like, but anyway, they take the reading at 45 and then they invert it 180 and take another reading. I didn't know.
Yeah, they want to average out any bias in the
Yep.
in the setup.
Yeah, got you. So that's where we get the 15 degrees per hour, or 15 degrees per hour, in regards to the gyro, and what it, the text or whatever, right? So,
yep.
Okay, so moving forward, we have 2 other examples of single axis gyroscopes and their respective correction angles. So this is the Ginger project. It stands for Gyroscopes, Underground, and General Relativity, or something like that. It's some acronym. It's whatever. Anyway,
Okay.
these are their apparatuses. They have them at their 45-degree angle corrections, and this one is located in Italy at the 43rd latitude, and then there's a station in Germany that's located at the 49th. So all around that similar area where it's like, is it a globe? Is it a plane? Because in the flat, this is where we'll get into the flat Earth side of the vortex, right? So on the flat Earth model, it would just be your standard Gleason projection, right? And azimuthal equidistant projection. So kind of conceptualize that and kind of think of it from a, I don't have a slide for this, I apologize, but just kind of think of it like, a 2D view, like you're looking at it as it's like, laid down like a pizza, right? Like a floating pizza in space. You guys, I'm sure you guys can conceptualize that, right?
Your words, not mine, but yeah.
It's just for the visual aid, bro. It's all good.
Yeah, sure.
I'm just
we don't have to get uptight about it. Yeah.
No. Yeah, I'm just messing. So
yeah, you're fine.
Yeah, so just kind of conceptualize that, and then from the center of that, there's a ether vortex. There's a stemming out from that center point, right? And it's all encompassing the disk that we live on, right? And it rotates east to west, follows an east to west rotation, and that is what they're measuring. So if you're on a plane and you want to align your device to the thing that's rotating, if you're on a stationary plane, well, the sky's the thing that's rotating, right? So you're going to correct your device at the same situation, at the same latitudes. So in these same respective places on a plane, so far there's not in any distinguishing correction angles or readings that would facilitate like symmetrical readings on a globe and also the correction angles.
Yeah, you lost me there.
Okay.
You just said 2 things that I don't understand.
Okay.
But what I want to focus on right now is why, if we're on a pizza world, why do we have to tilt the device at the same degree as your latitude? Why is that? See, on the globe, you have a diagram and you show why, because it's a globe. Why on flat?
Okay. So the sky above us is rotating. So if you kept your device aiming at the not rotating part of the thing, you wouldn't get the good reading. So if you tilt it up towards the sky, it's where you start to get your readings.
Are you saying that the sky is not directly above me?
Are you saying that if you were 45, if you were at the 45-degree latitude on a globe and you were at the 45-degree latitude on a plane, if you were aligning it to Polaris and that was your way of aligning it to ensure that you were correcting it to the axis of rotation with the Earth, how would you distinguish the difference between the 2 correction angles if they're the same for a single axis gyro?
Okay.
In both places?
I have some slides that might help explain my question, if I could. You don't mind?
Okay. Yeah. Let me pull you back up.
Let's see here. Let me just share my screen. I'll share that one, and then we'll bring this up. Okay. Okay, I have to put myself on. Bear with me. I am my own producer.
You should fire that guy.
Fire this producer. Okay. Yeah. Am I screen sharing? Are you guys seeing that? No, it looks like that's not working. Oh, here we go. This is what we want. Fire that producer. Dang. Okay. Here's a bicycle wheel. So to keep things non-controversial, it's a bicycle wheel. And it is rotating like the green arrow shows. So if we were to measure rotation using a gyroscope at the hub, we would get rotation parallel to, we would get an axis of rotation straight up and down, perpendicular to the plane of the wheel. And if we measure anywhere else on the wheel, we still get perpendicular rotation, like so. Anywhere on the wheel, the axis of rotation is the same, and the rate of rotation is the same. That's what happens on a bicycle wheel. So I think you're telling me, let's see here. You're telling me that on our flat Earth, we do not get the same axis of rotation everywhere on the wheel. We get different axes. Is that correct?
Yeah, that's my suspicion. That's why I think that there's not any single axis gyro readings in the South that are publicized and talked about.
Well, but do we agree that physics does this? That this is, if it's a single rotation that's uniform throughout, that we will measure it as uniform throughout. We do not have to tilt these little gyros in order to measure the rotation.
Okay.
Okay, so that's how a bicycle wheel works. So then what you would ask me is, why would it be different? Why wouldn't it just be the same on a sphere or flat? This is why it's different, because
it would be the same on a sphere.
Right? On a sphere, everyone is measuring the same rotation. It's just they have rotated with respect to like the axis of rotation.
Well,
but
before we could
here, we should get the same axis of rotation. So my conclusion is there must not be a single axis of rotation that is shared by the entire Earth. Is that right?
Yeah, I disagree. There's a all-encompassing ether wind, and where you're measuring relative to the latitude, you're further away from the source of it, and you're measuring the increased speed of that. That's what interferometry is picking up. That's what's causing the variance in the speed of light with interferometry.
Okay.
That's why that's what this effect is measuring.
I think you're screen sharing the Zoom right now.
Oh, apologies.
Which is okay. I mean, I tried to put you back on.
Oh no, you're good. You're good. You were talking, and then I was waiting.
So I think that's what I need explained. I've shown you my diagrams of how I explain what I expect.
Yeah.
Now you explain to me where that was incorrect and why.
So before we could even substantiate your diagrams, though, we would need readings at those latitudes to even verify that there are symmetrical readings all across the globe. As I showed you, I could only find instances in 3 areas, and they're all at the same latitude, roughly.
That's a separate point. I think it's a good point. You showed 3, and they're all in the northern latitudes. They all happen to match exactly their latitude.
For both
but
models.
It's 43 degrees and 49 degrees, right? So I mean, like, whatever, right?
My point, exactly. So we're talking symmetrical readings on the globe, like in the southern hemi, right? So you're talking some people in Australia, some New Zealanders, maybe.
But isn't that enough for us to agree that that it's not the same everywhere on the surface?
Come again?
We can agree that at 43 degrees in, where was it? Somewhere in North America. And also at 43 degrees in Italy, they both measured the same rotation. right?
Oh, yeah, that's not my point of contention. We're talking
But no,
going
this
further
is,
away from those.
I think this is enough. This is enough. We don't need to go to the southern hemisphere because
Mm.
they both tilted like so. They didn't tilt like that. They tilted like this. One's in Italy and one's in North America. So
Do you
they're
think it would
not
be? Do you
parallel.
think? Do you think it would be different on a plane at 45 degrees when you're aligning it to the sky?
I think, I think,
If the center axis of rotation is at Polaris or something like that, then like yeah, that's why the readings would be the strongest because they do the same on the globe. Those Ginger projects, they say that they're aligning it with Polaris on the globe relative to where they're at. So like it's literally the same exact thing as a plane at that latitude, right? So when you
I
want to
think,
draw, yeah, go ahead.
I think that if you have a single axis of rotation, everywhere on that surface that is rotating measures the exact same rotation. But you
Agreed.
said, let's ignore this one. Let's just take one and imagine this is Italy. Imagine this is North America.
Mhm.
Those are not the same axis of rotation.
So they're both tilted. They would both be tilted in the same way, bro. Like I don't understand what
Do
like
those look tilted in the same way to you?
oh, that's your model of how you think that they would be tilted. Like they were both are 45-degree correction angles that like you
But
just
they're
tilted it
not.
on a different angle
But
because
they're
it's
not
on the other
parallel.
side.
Are they
Dude,
parallel?
are they both aligned to the axis of rotation in the northern hemisphere relative to where they're at? Yes or no?
I'm sorry. Say again.
Are they both aligned to the axis of rotation relative
No.
to the latitude where they're at?
No.
No, at the 45 degree, but only
No.
on a globe though.
On a globe, they are.
Okay,
On a.
that's fine.
Do you understand why?
I think you don't understand why they're the same, but continue.
Well, no, I don't. What I'm trying to say is that on a globe, they are those axes are parallel. They're literally parallel, right?
You assume that you're aligning it with with a hypothetical axis that goes down the middle of the globe. I'm assuming
Right.
that you're just aligning it with the sky. There's no difference between our just two models at the latitudes that are provided.
The difference is in the globe model, we align them all to be parallel with each other. They're all one axis. But in the flat model, they are not parallel. There's one in Italy tilted 45 degrees towards Polaris, and there's one in Northern America tilted 45 degrees towards Polaris. How can this be the same axis? That's not parallel.
It's pointing to the same axis of rotation, my dude. Like you're just
You're
assuming that
saying,
the
are
axis
you
is in
saying
the
that they
ground.
rotate like this? That they don't rotate like this, right? They don't go this way. They go this way. They don't go
What?
like this. They go like this. So they're barreling around the surface.
No.
Like, okay, let me try a pen.
Uh-huh.
So here I am. I'm like in Italy. I'm pointing to
Yeah.
Polaris. This
Yeah.
is the rotation.
Uh-huh.
So that cannot be that the sky is going around. That's not what, that doesn't do this, right?
You're
That's
lifting the device off of the ground and aiming it towards the sky. If there's a vortex that goes down to the center of, or goes down to the North Pole, right? Same thing. That's what they're aligning it to. As they get further away from it, I suspect that the readings get stronger and that they're not symmetrical for the globe. I suspect that it increases and that it's picking up a increase in speed in the ether wind.
okay. When you say same thing, what do you mean?
The correction angles are identical on a globe and on a plane at that latitude. There's no
What,
distinction between the way you're aligning it with the hypothetical axis of rotation or the way that I'm aligning it with the hypothetical ether that's extending, an ether vortex that's extending down from the sky.
okay. Why? I can explain to you why we align the way we do on a globe.
I
They're
just did,
all parallel,
yeah, I just did the same thing to you.
but no, they're not parallel. You must agree. Hopefully, you agree they're not parallel on a flat model.
They're aiming at the axis of rotation of the sky. This is the same position that they're orientated on the globe. Yes or no?
No.
You
Incorrect.
just showed me that they're 45 degree at the 45 latitude. If there's a ball in between my hands, this is at 45. This not the same? Continue.
Teacher, sir, I'm sorry, but you cannot aim at an axis. You can aim at a point, but you cannot aim at an axis.
My dude, axially aligned.
Okay, then that means parallel, not axial aligned. Alignment means parallelness. It does not mean
if the ground isn't rotating and you lift the device facing off of the ground, it's facing this, it's going to the sky. That's it. They're identical correction angles on the globe. I know it sucks.
Shouldn't be. That's what I'm struggling to understand. Why do you think, how do you justify that they are the same angle?
How are you not justifying that an all-encompassing rotation of the ether relative to the latitude wouldn't produce a varying speed the same way they say at the 45th latitude, you're spinning at 750 miles per hour. At the equator, you're spinning 1,000 miles. How do you not see the difference between the rotation of the ether and the mechanism of the turning of the globe being identical in that regard, especially when you're drawing your conclusion based off of correction angles at the 45th latitude?
I didn't follow all that. Can you say it back slower?
Yes. So how are you drawing your conclusion that you're aligning it with the globe if it's identical to lifting the device to correct or to aim it at the sky to get the reading of an all-encompassing ether that would produce the same effects that would be, you know, how they say, hey, we're on the globe and you're at the 45th latitude, you're rotating at about 750, even though you can't feel it, blah, blah, blah.
Okay, let's pause. Let's pause there. No, rattle on.
Sorry.
How do I justify that I'm aligning something in the globe model and I can't justify that same thing in the flat model? Is that what you're saying?
The correction angles would be identical, so I don't see why you're getting caught up on it. According to an ether model that you're trying to confine yourself to, though.
You must have a different model. If the model is, okay, let's say the Earth is still and the ether is spiraling around us. Okay, if the spiral is like we're sitting in a whirlpool, right? If there's a single axis of rotation, like a bicycle wheel, then everywhere on that surface is experiencing the same parallel rotations. So if they are not experiencing parallel rotations, then that means we are not in a swirling uniform.
If the Earth is stationary and there's a swirling thing over top of it, the stuff that's furthest out from the central axis of rotation is going to be going faster than the stuff that's closer. That's the variance. That's the variance in the readings. So your whole thing.
The angle.
Okay.
We're talking about the angle right now, right?
It's axially aligned to the sky. You're confining the detection of the ether vortex, you know, blah, 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 to like however you need to, so that you can't see it, like so that it doesn't make sense. Like I don't get how you don't understand that they're aligning it to what's
okay. Let's back up. Let's just talk about the bicycle wheel. Okay. Let's not talk about anything that we're bound up in with our beliefs, right? Just a bicycle wheel.
Okay.
The axis of rotation is the axle that goes through the center of the wheel.
Yes. Are you placing the observer on the wheel or not?
No, let's just, we're holding the wheel. We just spin the wheel.
Cool.
The wheel rotates around an axis. The axis is a line, an infinite line that passes through the hub.
Okay. I think you're confused on the effects that are being measured here. Like, let's sidestep the.
Well, hold on.
Because I think this will help with the corrections. Okay, yeah, go ahead.
What I'm stuck on is the words you're using. So I want to get them better defined so I understand. So we understand each other. So an axis is a line. It's an infinite line. That is an axis.
Yes. For example, like the cosmic microwave background.
So you cannot point towards a line. And if you align with, that means you are parallel to.
Mm-hmm. And if the sky is above you and you're tilting your device up,
Now, see, as
and
soon
the
as you start the sky, you change the rules. When it's a bicycle wheel, we can understand that the axis is a vertical line going through the hub.
okay,
So anywhere in the world, another vertical line that is aligned to, here's my hub, here's my axis, here's another, this is aligned. This is not aligned. This is aligned.
all that would do then would just change the nature of the vortex from being connecting to the Earth. That's all that that would remove, and it would just be that it's axially aligned with the, or with the sky. Then that's all
So
that it would
they
change in that regard.
so my understanding, and I think is what you're saying now, is that the vortex is not a simple whirlwind rotating around a single axis, but is instead twisted somehow so that
No, I just said
it's
it's
got
not
this
connected to
axis
the Earth.
here and this axis
I-
here.
I'll clarify. I just said it's not connected to the Earth in the way that I conceptualized it. You make a good point.
How is it connected to the Earth then?
Well, the way that I was conceptualizing it is that the vortex was stemming down to the Earth, and that there was a physical connection. But you make a good point about the alignment. That is a good point. So it would just be aligning it to the sky, then the thing that's actually rotating, without a connection to the axis. That would explain it. That would explain the not parallel exactly angles on the globe.
Well,
The
you
way that you're
just said
talking.
aligning again, and I'm so confused because to me, aligning means parallel.
Aligning in the same way that you're doing it, just on a plane, dude. The same thing, just different axis, bro. You think that you're parallel to the axis of rotation. It's not.
Right?
Or I mean of the Earth, right? I think it's just aiming it towards the sky and it's getting the readings, because
But
that's all that gets
the
measured.
sky is everywhere, right? You're aiming towards a particular point in the sky.
Well, there isn't there the sky does intersect with the whole entire universe intersects with Earth's axial tilt or the sun's ecliptic. So if we're talking about the rotation of the sky on that point, yeah, aiming it at the sky would probably produce a sidereal rotation effect, and that's what they all measure, which we
Okay,
can get
so
into later.
I think I heard that we aim at Polaris essentially. I mean, it's a couple degrees off, right? But where Polaris is the point that we aim at to get. Is that right?
Yeah, to be axially aligned with the Earth's rotation, or
Oh,
to tilt
the
your device
ether
to the
rotation.
sky. Either one, indistinguishable at the 45th Laddie.
Okay, and it is indistinguishable because not here. And this is what I'm really stuck on. It is indistinguishable not because we had a model that made this prediction, but instead because we made this measurement and we are now building a model that matches that prediction.
Mm-hmm.
Right? So in the globe version, we have a model that makes the prediction, but in the flat version, we are trying to build a model based on the observation.
Yeah, trying to piece it together. Yeah.
Okay.
I see how you're trying to frame it. Don't give a shit.
Yeah, no, you know what? I'm not trying to be controversial. I'm trying to come to an understanding, and I'm back to I think that the ether must have rotation that we measure that is tilted at different angles on different parts of the Earth, and that those axes do point towards what we call Polaris, right? The axis of rotation here and the axis of rotation here. And so the model that we're building is not just a swirl, but it's some kind of, I mean, Stephanie says it's a torus field. Not,
I wouldn't describe the ether to the magnetic torus field movement. Like, I wouldn't know how to map that. The way that I conceptualize it, just based off of the readings and the effects, is that it's a uniform field that's rotating with sidereal time.
what do you mean by uniform?
So on the bike wheel, like the spoke is connected to the axis kind of thing. So like that, like it's just, all sweeping across like a big stream.
But I think we can agree that it's not like the bike wheel.
No, we can't
So
because
it's not uniform. So we should drop that word.
What's that?
It's therefore not a uniform rotation. It's always 15 degrees per hour, so that's uniform.
That's yes.
But the
And
direction
the
varies.
measurement that you get out of it, I'm sorry, you're okay. Let me rephrase. The measurement that you get out of it varies.
Right. So it's not I don't know if
The
you
e-
call
the
that a
ether
uniform
the
field.
ether is uniformly rotating. The measurement that you get out of that based on your latitude is going to produce a variance in the speed of light because that part's moving faster, right? If you're further away from the center.
Okay. So just to make sure I heard you right, I think you said the ether is rotating above us in a uniform way. And I interpret uniform to mean like a bicycle wheel.
Follow sidereal time.
How does sidereal time fit in to a uniform rotation?
That's all the measurements that they make. So you know how they say the globe rotates at 1,000 miles per hour roughly to produce its effects. That's a uniform rotation roughly. So that's kind of the idea. That's kind of the same exact thing. That it's just uniformly rotating. The effects they measure relative to the latitude is the variance in the speed.
Okay, and sidereal time, you mean like a sidereal day?
Mhm.
Okay. Yeah, sure. Yeah, all right. That makes sense. Yeah. A sidereal day, not a solar day, is the rate that we measure of rotation. Yeah. Okay. I think that's probably as good as we're going to get. Is there anything further we can do about this?
No, that was good, man. You raised some interesting points. And, it's always good
Can you
to
bring up your
rethink things
slide
on the back
again
foot.
with the
Yeah, absolutely.
torus? Well, the torus, I don't know. That's kind of a torus, I think.
Oh yeah, this is just artist rendition, like visual eye candy. So like,
Maybe that can help us to understand what I'm talking about how it must be a different axis of rotation at different places. Let me make it big here. How do I make that big? There we go.
can you see it?
Oh,
Oh, you're good.
yeah. We're seeing it. You're good.
Yeah. Well, let me put you over to the side here.
I'm not really sure what's going on in all this, but I think
This is just
kind of a donut-ish.
it's just
Right?
conceptual art. The donut shape isn't related to the
It looks
ether
like
effects.
It looks like the
Yeah,
magnetic field.
yeah. Can you hear me? Is my mic on?
Yeah, I hear you. You're still good.
Yeah. So the donut, like you can just like, disregard all that. This is just eye candy to show you, like, see how it's like transparently filled in a little bit, or like what's the word I'm looking for? A little opaque or whatever. It's like that's just to give you a visual for like an ether encompassing the Earth and rotating with it. Like all these vectors and all that stuff is just visual stuff, right?
Yeah. There's a lot of visual noise in this. It's not exactly
Yeah, it's not the best one, but my ability to do the Photoshop isn't great, so I just use my girl Patricia's. So
right. But I think maybe what this can help us visualize is the idea that it isn't just spinning around at 15 degrees per hour. It's got to be spinning like you can't see me.
sorry, one second.
That's my fault. It's got to be spinning like this, where like here's one side of the Earth, here's another side of the Earth, and that's the rotation that we're getting.
Oh,
So
I got you. One sec. Kind of
it's
like
got to be some kind of very bizarre sort of donut type of shape.
Yeah, what is with you in the donut, bro? You and McToon are like, are you guys all right?
I don't know. Stephanie said it was a torus field, right?
I know, but like you're like, but like you just can't say donut regularly. You're like a don't like you're saying something naughty. Like, what's up? You all right?
Sorry, dude.
Yeah,
Donut's delicious. I love me a donut.
Cool.
I mean, as soon as you got that up, I'll make you big there.
Yeah, I'm just looking for the where do I have that? I know exactly what you're looking for. Just can't
I mean,
I could never find it on
we
the
could build
spot,
a
but
map of it. Um, we could build a map of how it rotates.
oh, here you go. Here, check this out. What do you think of
Some
this?
kind of
This is kind
visual.
of this is an early conception of it, where it was kind of following
Uh-huh.
the like kind of flowing with the toroidal movement. But I don't know about all that, man.
Okay. Yeah. Is
Kind
this?
of
Did you draw?
loosely.
Okay. Yeah. Yeah. That's one of my slides, right?
Mhm.
Yeah. Okay. So yeah, that is exactly what I'm talking about, and you can kind of even see there's one in North America and there's one like in Russia, but that they're tilted on each other, and
Yeah.
that tells us that the axis is not just a bicycle wheel; it must be much more complicated than that.
So you're
Right?
saying there would be like different different flow rates within like an ether within the ether, so to speak. So like so the inner donut, I forget what they call that one. What's your inner donut? The hyperbolate or whatever.
I don't
You
know.
know what I'm talking about? You know the word.
Hyperbolic.
Anyway, the little mini donut, right? So like that would have its own ether wind, and then
Hmm.
the outward extending one would have its own. That was my early conception of it, but I didn't feel like that was I wasn't on that. I wasn't on board with that one.
Okay. Yes, way more. Okay, I'm going to put Stephanie's comment up on here. Yes, way more complicated than the pizza y'all make fun of. Um, right on, Stephanie. I don't think it could be as simple as like a pizza or bicycle wheel model, is what I'm saying here. If you want to build a model of this, you'd have to say it's complicated, and then you could build it, right? We could build a model that does this. Um, how would the flow be flowing?
Well, it would diverge and converge back at
Sphere
the
that we've
center, right?
unrolled. So this is flowing this way. This is flowing in a spiral.
Can
Yeah, I mean, you could build
you pull
that.
yourself up?
You could build that.
So
Oh
you
yeah.
like this one better than uniform motion? That's crazy.
Well, here's the deal. I like it better than uniform motion because the one you're showing now conforms with the measurements that you yourself highlighted.
Well,
But
hell,
the
then I guess I
uniform
like it a
motion does
little
not
better than too.
conform with what you showed.
Yeah. Well, that's good, man, and I appreciate you pointing that out because I totally had a different perspective on that because this was my original thoughts on it, but I was like, nah, this isn't like my the way that my problem with it personally was like I couldn't explain a mechanism for the motion here being different than than the motion outside. Why wouldn't they be the same? You know? So
Well, and honestly,
I was just like, why isn't it just the same then?
that's my why. When I ask you, okay, there's the what, right? This is our best available diagram of the what is happening. And then if I ask, well, why is that happening? I don't think we have anything like any kind of idea of why this should be the way it is. It's just that's the way it is.
Yeah.
Is that right? I
Yeah,
mean,
sorry,
and
you're good.
the Globers are all out there and they're screaming it into the screen right now and they're saying, right, that's why this is stupid. But to be fair, that's a perfectly reasonable way to approach science, which is to make the observations first and then try to build a model that describes those observations. And then we can start searching for the why behind the model. And that's right. That's the story of how gravity, right? Gravity, everything falls. Okay, fine. And then Newton comes along and he builds a mathematical model of how gravity seems to work, but he has no explanation. And then Einstein comes along with a more advanced mathematical model. And I made you small if you want to
Yep.
stop screen. There you go.
Yep.
Yeah, and Einstein comes along and with a more advanced mathematical model with a better explanation behind it. He's kind of got a why finally. And so if we're happy with doing science in that way, then we have to accept this ether vortex torus as following in that same thing. Right?
Respect, bro.
Okay. We would need to see what's going on in the middle. Space Miner, let's just throw it to you, Alan. Space Miner says, it seems pretty important at this point that we would need to see what's going on in the middle. Do you mean by middle, you mean like at the North Pole?
Yeah, he does.
That's the simple part. That's where they match, right? That's where the globe and the torus match.
So they say.
Okay, awesome. So I'm ready to stick a pin in that one and call that done. I think we both have improved our understanding of how this vortex model works and what its purpose is. Did you want to go on to something else?
No, I'm good, man. I appreciate the what's the word I'm looking for? The pushback on it, because I was thinking back on it now. Like, I'll rewatch it obviously and double check, but I'm picking up what you're putting down with that. So I'll definitely have to rethink some stuff on it, man. I appreciate that. This was a great conversation. And honestly, throughout the day, I kind of was like a little I don't know what's the word. We haven't talked in a while, and I was like, man, is this gonna go bad? Like, is this gonna be shitty? Like, so I was a little hostile earlier, but anyway, this was a great conversation, and I appreciate that. And for those of you who want to ask these kind of questions and get pushback and find out, like, where the limits are on what you're putting forward, versus what the mainstream says in the in a constructive way, definitely hit your boy up, man. So thank you for that. I appreciate it.
All right, cool. There was something you wanted to talk about. I've totally blanked on what it was. I think it was measurement arms.
Oh, that was a joke, bro. When you said that, I was just like spit back and forth. That wasn't.
Okay.
We don't have to.
Okay, you weren't serious about that. Okay.
No, that was just in jest.
That's
thank you though thank you for taking it seriously. Yeah, I apologize. I should have, dude. I almost sent you a message to be like, I was just kidding. Like, you don't have to do any research on that or anything.
Okay.
But I was like, he probably gets it right. But yeah,
I don't think I really prepared much for it, but
yeah, it's all good.
Okay. So I guess we're pretty wrapped up. You want to take any kind of questions from? You're on your chat too, right?
Yeah. Does anyone have any questions for I Can Science That from my chat, or if anyone has any questions for me from his chat, hit me up. We can do a quick 3 or 4 minutes on exchanges. Let me scroll through my chat and see if there's anything going on for you.
Yeah, see if there's anything that's actually like a legit question in here.
Give it a couple seconds. There's a couple
any kind of like constructive comment.
Yeah, what'd you think of the McToon debate? Was it good entertainment? Did he crush it?
Yeah, I mean, it's all right. I think I'm kind of disappointed with that format of debate. At least you guys aren't like, there's a question coming up. We'll get to it in a sec. At least you guys aren't like screaming at each other or anything, which is really good. That's a huge improvement. But you were both really just reading your notes.
Yeah. See, I agree. That wasn't the best. And so, I've been doing like presentations and stuff. And I started off just like, oh, just read the slides and all that. But that's not how you do a presentation, right? You have to know the material and just be able to flow it, right? And I should have done that with the stuff with the debate, but it was like very technical heavy, and I wanted to like say specific things like in a specific order, So I was like, I'll just read it from the thing and it'll be all right. And I totally regret that. That was if I could go back, I would summarize it way differently, and then jump into the conversation aspect of it way quicker. Totally agree with you on that. But yeah, the format, the way that I kind of conceptualized it, because like the modern day debates and stuff are always like super under what's the word I'm looking for? Like it's a
Under moderated.
yeah, under moderated, and there's a mismatch in like knowledge discrepancy because like maybe one person's like hyper specific on some area of this or that, and like but they don't know. So there's just kind of a free for all. Then you got two people that don't know about each other's subject. So I wanted to not leave wiggle room to be like, well, I don't know, or whatever.
Yeah,
So that's
I'll
why
say
we set
you
it up.
did a really good job of presenting like legit published research, which is pretty unusual. And so you were like the parity between yourself and Tune was pretty good.
Yeah, I thought so. I thought we were pretty evenly matched in that regard.
Yeah, I mean, I told you earlier one of the points I thought that you made that was one of your strongest was that apparently there were 14 corrections to the atomic clocks made,
Oh yeah,
and right, and I was like, yeah, I want to see that. I want to see because my understanding, of course, is that the atomic clocks are accurate to a second in a billion years or whatever, right? They would not need any kind of corrections.
yeah, yeah. That's kind
And
of what they
so
tell
if they
everyone.
do need
That
corrections, I want to know how big is that correction?
yeah.
How often does this happen? Why is it? Why is it? And so forth.
So let me
So
link you. I can link you a couple of papers on atomic clock synchronization because that's what they tell us all, and we all thought that we're like, oh, cool, yeah, atomic clocks just go
it's
forever in perpetuity, but that's not the case.
definitely what we're taught. It's what the science textbooks say. We
Yeah,
do have a couple of knowledgeable professors here
yeah.
in the chat. If anybody wants to chime in on atomic clocks, my understanding is that they're obscenely accurate, and Alan is, I think, suggesting that they are not as accurate as we are being told.
Well,
So
it's not that they're not inaccurate; it's that they desync at varying degrees, and that keeping them
well,
accurate is kind of like a it's kind of like a trick using air quotes here. It's not like a trick, but I kind of explained it to you before. If you want a quick rendition, they keep cesium excited at a certain rate so that it oscillates at 12 billion times a second, and they use two counter rotating magnetic fields to keep it, within that parameters. And then
yes,
anything that's outside of that, it just gets kicked out of the field. And then they shoot a microwave at it to, keep it at that oscillation rate when it's losing energy. But it experiences decay at varying rates, and then then there's those random spikes that happen, and that's what Lewis Essen was talking about, like, the guy that made the atomic clocks. So like if anyone knows about random spikes and how they work and all that, it would probably be the guy that made it. But yeah, he talks about all that. And then further, when they get into Einstein clock synchronization, um, there's problems with it. And so the way that
so
they do,
well, hold on. I mean, before we go on in the whole like thing,
Mhm.
what I heard you say there was they're amazingly perfect until one of them just sort of jumps.
Well, no, they're constantly jumping. Like these are that like that microwave energy and the magnetic field situation. Like these are
Yeah.
constant corrections to keep this going. Like it's
All
not like
right.
it just does
So
it in perpetuity.
yeah,
And
but they
then
can't like fudge it using that. They can only hold it at a steady rate, right?
no, I'm not saying that that's where that's where the problem is. So the way that they make these corrections, like I was going to show you this paper by Paul Marmot, where he shows the equations that they use for the corrections. It's basically the way he breaks down. It's just the Sagnac effect. Like they're just correcting for the like the first order movement of the velocity of the craft, whatever it is. So that's all they're
Okay.
doing to
Well,
do the corrections.
I agree with that in modern understanding that the clocks need to be held in sync. They need to be corrected for various relativity situations.
Sagnac effect's not a relativistic effect.
Yes, it
None of
is.
the Oh
Well, I
yeah.
mean, I'm sorry. I should say it's taught that way.
Yeah, it's taught to you.
You don't agree with relativity, so of course you're not going to agree to that. But the mainstream
Should an
narrative.
inertial observer see a variance in C?
I'm sorry. Let's come back to it. Let's answer Space Miner's question, and then let's come back to that. Is there a correlation between moon and field models? I I don't know. I don't think so. Right?
Couldn't tell you.
I don't think there's no correlation between how the moon acts and the toroid of ether, right?
Not that I'm aware of.
Did you have anything else to say about that one?
Not that I'm aware of.
Okay. All right. So back to you then. You were saying the Sagnac effect, and you had a question about it.
Yeah. Should an inertial observer see a variance in C?
No.
Okay.
Special relativity says that an inertial observer measures C in a vacuum, C, always the same. That's what SR is supposed to say. Yeah.
Is a device
Sagnac,
in uniform rotation not an inertial observer according to special relativity?
It is non-inertial. Rotation is non-inertial.
Have you seen Einstein's thoughts on the matter? Like,
Yes.
okay.
And he
Why do
was
you
very
differ?
clear
Why do you?
that
Oh, let me. Okay.
you can run this. This is done in probably freshman physics. I mean, freshman college level. It's in undergrad college level. We do this
Mhm.
in modern physics. You take the course, you do this. If you simply measure the distance traveled around clockwise, measure the distance traveled around counterclockwise, divide by C, Sagnac effect.
Mhm.
It's simple as that. The inertial observer, the outside person who is not rotating,
Mhm.
can do this, and it's straight up.
Yeah. So Einstein says that if you're not, or if you're in uniform rotation, then you're an inertial observer. His equations hold true in that regard.
Yep.
So if the device is rotating uniformly, then it's an inertial observer.
So the
Special
Sagnac
relativity
thing, the
disproved.
inertial observer is the person outside the rotation. And so
Oh, okay.
when you watch, right, you watch the rotation,
Gotcha.
and that person is then inertial. The observer is inertial, and therefore you don't have to do any of the fancy stuff. And you can just run regular C equals distance divided by time.
Okay. Well, let's try. So you're saying that so first of all, the observer, where the photographic recorder is, determines where the observer is. So an observer watching the experiment would not be the observer on the rotating the device. The observer on the rotating device that's rotating uniformly would be the observer.
Let me clarify. I'm saying that in order to simplify the mathematics so that there is no question of how to do this, right? According to relativity, if you are rotating, the mathematics are complicated, and we don't want to do that in undergrad physics. But if we simply place an inertial observer outside the rotation, we can work the math from the perspective of that person.
Oh,
that
okay.
result must be
I got you.
shared. That result must be the same
in all frames
as all frames.
Cool. All right. Can you put me up on big screen? Let me show you this real quick. You're gonna love this.
Okay,
This is crazy.
going up on big screen.
This blew my mind. This blew my mind, man. So check this out. This is your boy Dufour and Pruner, two Frenchmen in 1942. What they did here is they reproduced the Sagnac effect of 1913. Nothing too crazy there, right? So no violations of special relativity as according to the textbooks, as just stated. So here's the configuration of their device. Now they make the argument, and there's other experimental evidence for this as well. But let's just go with what you said, that the photographic plate here, it doesn't determine that it's an inertial observer. You have to be off the photographic plate to determine the inertiality of the frame. Yes or no?
You have to be off the photographic plate.
I'm sorry. You have to be off the rotating device to be an inertial observer, right?
Truly inertial.
Correct. Okay, cool. All right. So they did a couple configurations of this experiment where this is the second configuration, where they took the source of light and they put it on the lab wall, fixed frame, station, an actual inertial source, right? And then they have a collimator here and a collimator here attached to the rotating device. This refocuses the light beam so that it can complete its circuit. And then it hits your boy photographic recorder right here. But as we were talking earlier, this is a non-inertial frame according to the textbooks and whatnot, and according to making the mathematics easy. Yes. Okay.
Sure.
So and this produced the same effects as the Sagnac effect in the traditional configuration. So
It
still
should.
in a
That's what
yep. So
SR says.
yep. So still in alignment with special relativity.
Okay.
And then here's the fringe patterns for this for the comparison. So it's exact identical.
Okay.
And then they get into this really interesting configuration here. And this is where they have a stationary light source here. They have a photographic recorder here as well. And then they got their collimator here to refocus the beam. And then they got a stationary platform right here, right? If you can kind of see my hands. So stationary platform here with mirrors angled at 45 degrees. The light comes in, hits the bottom 45 angled mirrors, and that's on the rotating platform. So the devices, or so the path of light is going to go from the stationary lab frame, hit your boy's stationary beam splitter, deflect off of these mirrors, completed circuit, go back, and then here at R, there is a photographic recorder placed as well. So it's going to take a measurement here for an observer on the rotating device, and it's going to take one for the stationary observer on the lab frame. Make sense so far?
Yeah.
Okay, and these devices are not connected. They're separated by 4 inches of nothingness. So the rotating device is completely independent from the stationary device. And then let's see. So this is the original conception of the configuration. They had to make a couple modifications or whatever, but this is the end result. Same exact configuration, lab frame, blah, 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 right? Then you got C here, which is just the central axis of both platforms that it's rotating. Here's a quick snapshot of what it looks like. So they're separated by 4 inches. The top platform, stationary, non-rotating. Bottom platform, rotating at 1 turn per second. And what they showed here is that the fringe shift for the lab observer shows a first order dependence on the 1 turn per second of the rotating platform. And also
are you telling me that they took different pictures?
What's that?
That they're looking at the same target and see different things?
No, the inertial observer on the wall, right, sees a fringe pattern based on the rotation of the rotating platform that it's not connected to in any way.
I don't see that there.
Yeah.
Is that 146 or 142?
142.
142, I see no fringe shift.
Yes, there is a fringe.
There
and
is?
Then, yes. And it's identical to the one that's on the rotating device. And then they get into it's crazy, dog.
I don't see that. In the picture you just showed, I would not confirm that.
Okay. Well, they've got their data, and then like Paul Lavue, anyway, we'll get into it. So this is what they showed with their observations. This is what they got.
Okay.
And they go over
what is the upshot you're going to tell me?
Yeah, so they go over the relativity prediction. So as you were saying, with the convenience of the frame, for the mathematics sake, right? Paul Lavue chooses the central location, or like the center of the rotating platform. I'm sorry. Let me rephrase. So for special relativity to derive the effect, it chooses the location of the rotating platform and it derives the effect. Cool, no problems, right? But if you put the if you calculate the distance from the from the traditional Sagnac configuration, so instead of being where it would normally be, it would be at the location of the photographic recorder on the device. So if you do the fringes from there, the classic theory predicts a fringe of 0.053 in the fringes, and relativity predicts 0.005. Like it's not able to show to make the prediction. Like, so in the way that you were saying, well, they just choose it out of convenience because the math's too complicated. Well, it didn't give the prediction unless it uses that preferred frame. Like it violates Lorentz symmetry in that regard, and it shows that the speed of light varies for an inertial observer. And then all Paul Lavue had to say on that regard, and I don't know if you know who Paul Lavue is, but we can touch on that in a second. But all he had to say about the matter was, well, if the device is rotating, we have to choose the center of rotation, and that's all I have to say about it. And then he dipped. So he had nothing to say to counteract that.
So your upshot here, if I'm hearing you, is that according to this guy, changing from an inertial to a non-inertial observer changes the observation.
Well, no. The inertial observer.
Hold on. we don't have time to go through an entire paper here.
Oh, okay.
What I said was about the SAGNAC was
Mhm.
you can arbitrarily locate your observer anywhere, work the math, and
Yeah, but
when you
you
take a
can't though.
picture of the fringes from
Right.
any observer, they should all see the same fringes.
Yeah. And if they
Now,
don't though,
you're
what do you
saying that they don't.
yeah. They see a
Okay.
variance with a first order dependence on the rotation of the platform.
That would be really interesting. I'm not aware of that, although it seems like perhaps it could be possible. I know that you know
I'll tell you
SR
what.
claims or
Yeah.
GR even claims to that if you're accelerating, then time varies and therefore events look different, but doesn't seem like you could take a picture of outcomes that are different in different um, in different reference frames. And if somebody, any of you guys online knows better, tell me if that's so. Seems like there's a paper from 42 that said that.
Yeah, it was done by DeFore and Pruner, 1942, and then also, like I was saying earlier, Paul Lavue was made aware of this experiment, and he like flew in to talk to these guys about it. You can read the whole thing; it's very interesting. And his answer to it was basically to just kind of say, well, we have to choose the center because it's rotating, and then that's it. But the observer is inertial, man. So like I don't. It's I don't know.
That's interesting.
Check it
It's
out. Let me know what you think because it's a new one. It's a new one, man. Like I know a lot of people.
I
It's a new interferometry thing. So
I'd
check it
probably
out.
go out on a limb and say this is,
Hmm.
it's an aberration. People
Mm.
have done all kinds of experiments over the years, and
Do aberrations
I'm
produce first
pretty in the
order
box
effects
with
though,
my
or no?
I'm pretty in the box with my perspective on it. So
Yeah, that's
uh,
cool.
I tend to think that we get aberrations from time to time, and then the ones that can't be reproduced or are explained in some other way, we move on and we don't go back to them. That's not what we teach in class. We teach the ones that work consistently. But I guess your whole perspective is that that hasn't happened in this case.
Well, it just shows that the speed of light is not the same for an inertial observer as it would have to be, as claimed by Einstein.
Okay. Yeah, we should do that next time. It's 9 o'clock and we could wrap up. But yeah, that was definitely something McToon wanted to get to.
Oh, dude, he wanted to get to it by saying that he disagreed with it, even though like the math and all
Well,
that like
he,
facilitates the first order effect. It's not
well,
really
well, no, he
anyway.
has an interesting point about like all the various interferometry experiments and whether they show a difference. And I think you like to point out that they do show a difference,
Yeah,
whereas we
at
are
the
taught
earth.
that they don't. Right.
Yeah. Well, isn't it weird though that you could just like look up and see that they do, and then like
But
that's weird
I
that they
look up
teach you
and
that
I
they
don't
don't.
see that they do. I
They
look at those
do. They
papers and I see
specific.
noise.
They say that. Oh, I got you. Okay, word.
Right. And when we look at the paper together, we both see
Yeah.
noise. Right.
Sure.
Let's not mince
Got.
words. They are noisy as
Okay.
all hell.
Okay.
And so what Miller did in
Oh,
particular
you
was
still
he
got me on
averaged
the
out
big
his
screen
noise.
if you want to put me on the little one. No, that's not what he did at all. But that's
That
cool
is
though that you think
absolutely what he
that.
did. He got
No.
noise.
Is that what Marisa Elias did when he analyzed it too? And then James Demio?
Yeah.
Were they just analyzing his repetition of noise?
Yeah.
That
Well,
shows
I mean,
that
you know what
shows
I
a
mean by noise,
fluctuation
right?
matched with sidereal time? Like I don't
That's not supposed to be a controversial statement. Do you not agree that it was noisy?
the way that I was interpreting what you were saying is that it was a nothing effect and that he
It was
extrapolated nothing.
it noisy means that oh, you're on full. Yeah.
Yeah.
um,
Yeah, there we go.
noisy means like here's a not noisy signal, right? Not noisy. Here's a noisy
Mhm,
signal,
mhm.
right? Um, Miller's is noisy. It jiggles all around, right? It's
jiggles.
not a smooth curve. It is very bouncy.
What?
Right. And so that leaves a lot of room, a lot of wiggle room for the two of us to interpret it differently. Like I could say it's too noisy to interpret that as the pure signal inside meaning anything. And you could say that when we smooth out the noise, the signal is underneath there. And I think that's why people can both look at the same paper and interpret it differently.
Yeah, man.
Okay. But there was something McToon wanted to say, and I think it's a good point, and that is Miller came up with a direction and magnitude for the ether wind.
Mm-hmm. Of an Earth moving at a velocity of 1,000 miles per hour, roughly.
Okay.
So,
I don't remember. I have it here, but I don't remember what it was. Do you agree with that?
No, the Earth isn't moving. He extrapolated the direction based on the effects that he was measuring. He mapped out the axis of rotation of it, so to speak, which actually, dude, I think you might be okay.
So wait.
Mm-hmm. He mapped out the cosmic microwave background, basically. But go on.
So Miller showed that there is a variation in the speed of light in different directions. Yes or no?
Yes.
And that is because of ether flow, ether wind. Yes or no?
Yes. Corresponding to the movement of the sun. Yep.
And it does not. That's not what Miller said. Miller said that it is pointing from a particular direction with a particular speed. Correct?
The fringes reach their minimum and maximum dimensions on the equinoxes. That's what I'm referring to. You're referring to the direction that you're referring to the directionality that he extrapolated out of that to assume that what he was measuring was motion of the Earth and not the motion of the sky. But continue.
Right. It was not constant. It was not a constant that Miller measured. You're saying the speed that Miller got varied throughout the year, right?
Mm-hmm.
Okay. And the direction also varied throughout the year. Is that right?
No. What do you mean?
No, just the speed. I'm not sure.
Yeah, I don't know
read that follow-up paper. Miller only gave one direction and speed, but the next person you quote reanalyzed Miller's work.
Yeah. So when they do the reanalyzation, like you got to remember, all these guys are going to interpret it as the Earth moving through something, right? But
well, okay, we don't have to go there, right? We can totally say that it's the ether moving past the Earth.
Yeah, that's what I'm saying.
That's fine. I'm fine with that.
Yeah, well, I mean, that's
what the direction and magnitude. Do you agree with it or not?
I agree with so let me pull up the model and show you what he mapped out. And I agree with this in the respect that if you map it to the sun's ecliptic is in alignment with the cosmic microwave background. I absolutely think that he mapped out the cosmic microwave background, because this blew me away when let me pull up this model real quick. I was like, what the hell? It's awesome. So ether, 1 second, pull this up. Wind, James Nimue. 1 second. It'll be in the pictures here. Yeah, right here. So yeah, this is what he thought he was measuring based on the axial tilt of the Earth and whatnot. But if we live on a stationary plane, then everything would just default to the sun's ecliptic. So it would be relative to that.
Well, hold on.
Mm-hmm.
We're going to bump into this again.
Mm-hmm.
It seems to me that if we live on a plane, there is no ecliptic. It's not a plane anymore. We've had to twist.
No, the sun's movement.
The plane of the ecliptic is now a Pringle.
No. The anal limit and all that would still be the same on the flat Earth. It's just the
plane
movement
of the ecliptic is the plane that all the planets move in, right?
Of the sun. Sorry, all with respect to the sun. So it would just default to that. That's how it is in geocentrism and a neo-tectonic model. It would literally be the same.
Right, but geocentrism and neo-tectonic, whatever, are both globe models. They're not flat models.
It's just mapping it to the sun and removing an axial tilt.
Well, but if you do that, right, if you unwrap the globe, just like what we saw with the ether vortex, if you unwrap the globe, things that were planes become twisted.
Well, luckily the sky solar system above us is already a plane, so we're good to go, brother.
I'm sorry, what?
What's that?
Where it's a
They
plane?
They all orbit on the same plane, all the planets and stuff, right?
Okay, but the planetary motion on a
Mhm.
flat Earth is not planar anymore, or is it? I guess planets don't move in 3D, right? Planets just move in 2D on that plane.
Yeah, I think so.
And the sun moves around on that same plane, right? It moves in a
Mhm.
circle, almost a circle, in that same plane. But the
Yeah.
planets do some weird stuff on that plane.
Yeah, let
So
me show
when
you.
you say plane of the ecliptic,
Pull up a video.
that's what you mean? The plane of
The
this,
sun's ecliptic.
the sun's ecliptic.
Yeah, let me show you this. So we got two things here. Let me see. Let's see. So you got your boy cosmic microwave background / movement of the sun, right? So over a flat Earth, that's how it's maintaining its altitude for everyone to see it in the northern hemis. That's what it's producing. Do you see that? Then I'll show you one more slide.
Yeah.
Okay. 1 second. 1 second. Oop, that's not the right one. Nope. 1 second. Sun movement. I'll have to come back to it. Give me a second.
I don't think we need to
me.
go into this much depth in order to answer the question that McToon is bringing up here, that I want to answer, which is the direction of the ether flow and the speed of the ether flow. Do you accept Miller's results of that?
No, the flow goes east to west.
Okay. All right. That is the key. That's the key question. And I'm going to say now, you accept Miller's findings that there is a flow, but you reject Miller's findings of the direction and speed of that flow.
Yes, he's mapping it to a globe. He's assuming that he's actually tilted and all that.
The globe or flat. All he gives is a direction into the sky and a speed that has nothing to do with whether it's globe or flat.
Did you not see his model? It's literally all based on the axial tilt of the Earth and the sun, based off of his data on the equinox, because it matches sidereal rotation.
That's fine, but unroll it, right? Unroll it onto your flat model.
I did.
And just take his direction and his speed, and it had nothing to do, his results had nothing to do with the plane of the ecliptic. They were outside the plane of the ecliptic.
So if the Earth were moving at 30 kilometers a second, they would have measured that in full.
And he measured instead what?
So he measured like just a little over one fringe, and they interpret that as 5 kilometers a second. So Miller being just over it, like slightly over Michelson and Morley's, they say that that's 8 kilometers a second. Now, that's tied to how they were trying to interpret it through the orbital velocity. When you just plot it to sidereal time, it matches within 98%, shows the fluctuations when you plot circular interferometry, so like a Michelson gale or whatever, right? It shows a 98% match to sidereal time. When you plot Miller's linear interferometry data against sidereal time, it shows a fluctuation corresponding to the equinoxes. And we know that there's a first order dependence on the rotation of a device, and with Ruyang Wang linearizing the Sagnac effect, we know that full linear motion would be detected. So if the Earth were moving in that direction as he thought it was, he would have got a much stronger fringe.
Okay.
So that's why I disagree with all of that.
That isn't what I asked about at all. None of that.
Well, that's why I disagree, though, because if you're trying to get me to like agree with it, I'm explaining why.
Can we answer what I asked about?
Yes, I don't disagree with it, because if the Earth were truly moving in that direction, the readings would be much stronger.
It doesn't matter if the Earth is moving or it's the ether moving. Okay, can we just say that? Let's not even talk about whether the Earth is moving or not. Just set it aside.
Yeah.
Okay. We should, if there is an ether wind, we should be able to measure the direction that wind is coming from and the speed of the wind.
Yes.
And Miller did that.
It's the speed of light is faster going east to west.
Okay, but that is not what Miller found. Miller
don't give a
found that the speed of light is faster coming from a point in the sky, not from east.
based on how he thought the Earth was moving when it's
Are you
not.
telling me now? Are you telling me that the direction he measured, he rotated it up into the sky for some reason?
No, the variance is shown in other forms of interferometry and in GPS, where it shows that the preferred direction is east to west. When you look at Michelson, Gale, Pearson, and that
Okay,
experiment,
let's
the variance
don't change
comes
the
from east to
subject.
west. The variance comes from east to
Okay,
west.
but Miller did not find that.
Don't give a shit what Miller found, bro.
Okay, then I'm
Like,
gonna pull it back on you. Then we're not going to give a shit about what Miller's found. You either accept Miller
in
or
regards
you
to the
reject
Earth motion, yes.
You don't cherry pick which results you liked and throw out the ones you didn't
I'm
from the
not
same data
in
set.
the I'm not in the full context
Okay,
of
so
interferometry.
Miller is we're
Hold on a
rejecting
second.
Miller.
Hold on. As in the full context that I explained to you, that interferometry would register the full amount if the Earth were in motion at that speed. It does not. That's it. So when Miller extrapolates that the direction of this and that based on all that doesn't mean anything. When it was reanalyzed, some guy found a different direction. Doesn't matter. You trying to tie me to that is making me disinterested in the conversation. I'm getting super bored with it. We need to either move on or talk about something else. As I've explained
Okay,
to you multiple times
I
now,
don't
that
I don't want to be
there's
I
a
don't want to
first
be
order
offensive,
dependence.
but I think you're
Mhm,
highlighting a real problem there. That
mhm.
if we can't talk about something because it stings, then that's a serious bias.
It doesn't sting. I've answered it adequately, and you keep
You
repeating it.
have not. You have told me. Let me echo back what I understood.
Mhm,
What I understood was Miller found the speed of light varies in different directions.
mhm,
And the direction that Miller found was wrong.
mhm. Based on him assuming that the Earth is moving
Then Miller
and
didn't
rotating.
find it. Miller's data is crap.
Not all of it.
Not all of it. Okay. All right. I think we better move on because you seem upset about that one.
I'm not upset. I'm frustrated that you keep repeating the same thing and you don't acknowledge that there's a distinction between measuring the full effect of motion and not. That's why I deny, or that's why
I
I
don't
don't accept
understand
his
that. Okay.
interpretation
Frankly,
of
I
it.
don't understand measuring the
Okay.
full effect of motion and not. Please explain
Okay.
without going on to these other things. Just in the context of a Miller experiment, what did they fail to measure?
Just in the context of the Miller experiment, you wouldn't fucking know and you would have to agree with Miller. That's why the full context shows that the motion that you need for the Earth to be moving doesn't exist. That's why I don't take Miller's reading as a direction of motion for the Earth. He assumes two different vectors of motion
Okay.
for his
Trying to be
interpretation.
as objective as I can be. Um,
Why don't we object
my,
to something else then
my,
and just move on?
okay, we can just move on to something else. Did you
Thank
have
you.
anything you wanted to ask me?
No, I'm good.
Okay. Yeah, that was really my other thing that I think I wanted to ask you about. Well, do you remember what the other thing I wanted to ask about if we it was the single axis? Yeah, I wanted you to explain to me why you want a single axis interferometer. No, not interferometer, single axis gyro. Because I kept saying like a 3-axis gyro is 3 single axis gyros. So
Yeah.
explain that.
So in the context of the debate, and not just the debate, but just overall, these correction angles are like, globe, or quote unquote globe proof, right? So to say that as if there's like rereadings all over the place and there's more data to like substantiate that claim and back it up, I was looking for that data, didn't find it. So like that's where the pushback was from that. So to supplement the lack of single axis readings, um, Toon said, well, we have inertial navigation systems which have multiple axes or multiple gyros per axis, blah blah blah. They do the readings, and then my contention to that was that this is it's a computer system that takes readings, has a data set that it compares it to. does all that, sends you an output.
Oh,
So
yeah.
so in
Yeah,
turn,
you keep referring to the Kalman data set, and I have no idea what that is. Could you please show?
Yeah.
What is the
Yep.
Kalman data set in context of an inertial navigation system?
Yep.
Yeah,
Gotcha.
that was what we were going to do.
Yep. So in the context of an inertial navigation system, we'll give a quick rundown of what it is and why my contention of accepting the output readings as proof to
Can we
supplement
go
a single
straight to
axis
the
gyro.
Kalman thing?
Yeah, sure. So the Kalman data set here, where's Kalman? Let's see, 1 second. Okay, the philosophy of the Kalman filter. So what this does, this whole data set here, what it's doing is when the device is calibrating, it's taking its readings and then it's like comparing and contrasting to the quote unquote known readings or whatever, right? And that's what it's doing. It's just narrowing, zeroing out like the noise, so to speak. Because what they do also is to prevent what they call frequency locking. I'm not sure if you're familiar with what that is. They vibrate the device to induce a fringe pattern, and then they zero that out. And part of all of that zeroing out and comparison and all that is facilitated by this Kalman filter, the Kalman data set that's in the inertial
Okay,
navigation
so
system.
a Kalman filter, let's go back to the Kalman filter. The Kalman filter is essentially a low pass filter. Am I correct?
What is a low pass filter? What is
a
that terminology?
filter designed to smooth out the noise.
On the surface level, that's what it says it's doing. Yes.
Okay, so as far as a data set, there's no data set with that other than just the parameters of the filter, right?
No, it's taking the readings and comparing it to the Kalman data set. So there's a data set that accompanies
Show me that.
this.
Show me that, because
bear with
that's
me
not what that line there said. The highlight you first showed said it was a
Yeah.
filter.
Let me see. Kalman data set. Kalman filter.
Sure, I don't want that. Clive is asking, a single axis will only respond to the relevant component of the angular velocity. Not sure why you would want that. And I think that would be very useful in that you could then tilt it around until you found the local maximum, which would then be the axis, right? You could find the axis of rotation with it, and I think that's the reason we would want one. Okay, and you're looking for Kalman data set.
Yeah, can't find it.
Yeah, I got a hint.
Can't find the terminology. Go ahead.
The hint is reread the Kalman filter. You're thinking of the Kalman filter, and I think you've misunderstood or conflated that with some kind of lookup table. The Kalman filter is a smoothing function to eliminate vibration.
Oh, okay. Yeah, we'll definitely reread that and take a look at it then. My understanding of it was that it was comparing the data sets relative to the latitude to make sure that it was getting the readings, at where it was at when it was doing its calibration.
No, because like this is just a gyro, right?
No, it's a computer system. Here's the schematics for it. It's
right,
a whole.
but the workhorse of it are gyros and accelerometers, right?
Mhm.
And so we use it
I mean,
to measure when the aircraft or whatever rotates, and that doesn't correlate with any particular latitude or anything. That's just how we get where your nose is pointing and stuff like that.
yeah. So then the way that McToon was even trying to apply the inertial navigation system wouldn't even make sense then.
Well, I don't know, how was he trying to apply it?
To supplement it for single axis gyro corrections.
Well, it's got three of them in there. Well, it's probably got more than three, right? Because it's got redundant ones.
Mm-hmm.
But they'll tell you the orientation and how the orientation changes over time. That's what it does.
Well, after you booted it up, told it where you're at, and entered your coordinates and all that through maps and or GPS locations, and it's calibrated, then it's going to it would produce whatever it would needed to as you move through the coordinate system. So, like for example, here they have a special mode when it hits the 45th latitude or 65th south latitude, it switches to polar navigation mode, where it uses an entirely different coordinate system set. So my contention was that if you were to take this device at the equator, for example, it would produce an output reading that would, supplement the single axis gyro corrections. It wouldn't contradict it, but you wouldn't know that it was being corrected on the back end because the coordinate system just switched to give you the relevant output. So that was my contention to it.
Okay.
And yeah.
So if I could say that back, then it's a complicated, and a full INS is a complicated, interconnected, programmed thing, and it does not give you the raw data of just what each gyro is saying. Is that fair?
Yeah.
I've even asked Wolfie whether maybe somebody on the ground crew can extract the single axis raw data. But I don't think we can. I don't think anybody can get that.
I've heard that it's classified to break to do that to those systems.
It's just not designed for that.
Yeah, and or that that it's like for the planes, for example, like they're not allowed to do maintenance on it. They have to take it back to the manufacturers if it has any problems with it.
Right. We don't crack those things open. I mean,
yeah. So in terms of like finding out, his point was like these single axis gyro readings, where you would have the raw data and all that stuff to confirm it would be that. So like that was my argument against it.
Clive is saying classified, but no, it's not classified, but they are sealed units. I think we can agree to that. I think they're sealed up units. You don't end consumers are not expected to repair or whatever those things. But if you get the cheapest you can get is a single axis gyro. You can get a 3-axis gyro also from the same companies, and they'll make you can get raw data from those. I think, does anyone remember whether Bob's was a 3-axis or a single axis?
It was a multi-axis. He had a $20,000 INS. Like, yeah, it had to have been. There's no way it was a 20,000 without 3, right? Like that'd be crazy.
I don't know. It may not have been 20,000. He didn't pay for it. He didn't know how much it was. Yeah, and I guess I wanted to bring it back to that. And that's something we've talked about before. I priced it out a little bit, and I looked on like eBay. You can get a used single axis gyro. You can get them for it probably cost you about 1,000, I think. By the time you got one, and stuff. So if we got one, right? If we did a little fundraiser and we bought one and we put it together, and then we did various experiments with it.
Dude, that'd be dope, man. That'd be dope.
I think it would be pretty awesome. It'd be a lot of fun. And then we would have to invest some more money, I think, because one of the things you said was you want to see the results south of the equator.
Yeah, I would like to see on the equator and south, because from my understanding,
so what we could do is we could ship it to somebody down south, or we could fly around the world, fly around the globe, have just an awesome time flying around, taking measurements. So yeah, maybe we start our fundraiser to fly around the globe and take measurements. But here's what, and people have offered to even fund it. Right, there are people with enough money that they would just plain fund it. And I told them no. I told them let's don't. And here's why: it's not going to change anyone's mind. And I want to say this again: would it change your mind? Would you care? What if we get 15 degrees per hour aligned, just like my diagram?
Before I had the understanding of interferometry that I do now, I wouldn't have cared because I wouldn't have understood it enough to give a shit. But I think it would be super significant and cool. Like, yeah, I would be totally into it.
Because
would it make me think that the Earth's a globe or whatever because of the readings? And like no, obviously not. But would I value the experiment? Would it be cool for you guys to do it? Would it provide mechanisms to back up a lot of claims that have been going on? Like, yeah, that'd be fucking dope, man. Like, I'm not gonna hate on you guys if the readings don't go my way. But I think is it gonna? Yeah.
I think it would be cool. It would be dope. I don't think, like you just said, I don't think anyone who's a flat earther would change their position at all. I think even you would change it from what I essentially understand is I'm not really sure what's going to happen past the southern hemisphere to, yeah, it works like that. But that's, I mean, we already got a twisting toroid vortex field. So why can't a twisting torus field do that?
It would be cool to have, well, it would be cool to have those readings to figure it out though, right? To see the geometry of it, because you could kind of extrapolate it that either way. Because right now it's just kind of abstract math based on specific locations in the northern hemisphere.
Well,
if you don't accept the inertial navigation readings, right? So
yeah, I mean, it's not like the fact that you can't find them doesn't mean they don't exist.
True.
They definitely do.
That's absolutely true. And if anyone finds them, please send them my way. My email address is alan.spaceaudits@gmail.com. Highly interested in those readings if you find them. That's not sarcasm, or like it was in the debate. I was kind of being a little, I don't know if you saw that. I was kind of joking around a little bit. But if you do have them, send them my way. I would totally, like, I then wouldn't continue to claim that they don't exist. So
yeah, I definitely think that they do exist. And yeah, you know,
yeah, we'll see.
They do.
Yeah.
We know how this stuff works. You know, there's
allegedly,
and there's, like, you know, it's not the only piece of data that aligns with that, right?
Yeah.
And you accept all the rest of it. So
I mean,
I don't know if you accept all the rest of it, but you accept the, you know, everything rotates around Polaris, and you understand we have to point at Polaris, and right. That's what that is. That's the same thing, right? Those diagrams that we made are all based on that. So what happens when you go past the equator and you're still trying to point at Polaris? Well, you just keep rotating at the same rate that you've been rotating.
Hypothetically. All right, man. I'm gonna head off here. It was a great show, bro. Thanks for chatting it up with me. Appreciate it. And you know, we'll reconvene at another time, man. Do it again.
All right. Thanks for coming by. Yeah, there's some nasty things in the chat here and there. I wish
I don't care, bro.
Thanks for coming by.
You gotta have thick skin.
And I want to repeat for anyone who missed it that we came up with a model of how the ether must rotate over a flat Earth. And it's a little complicated, but it should work. Right?
Yes, sir.
Okay. All right. I guess that's it. So good night, and I'll see you all next time.
All right. Peace, bro.
Bye.